It raises lots of questions, which will no doubt come afterwards. So we look forward to hearing your.
Yes, thank you. And first I would like to thank the organizers for inviting me to come. I'm the one of only two biologists here. Some of what I will say deals with biology, but you have to excuse me for that. I work mostly with thermophiles, but I guess that's why I was invited to come here. But I will first give a general overview of extremophiles, and then say a little bit about, I'll give a few examples of mechanisms they have developed to survive in extreme environments, and then talk a little bit about what we are doing in birkeland. Extremophiles is a very popular term now. It seems that everybody is working with extremophiles. But it's important maybe to define it. What is really extreme? Is it possible to have a scientific definition or just a subjective definition? We can have two different functional definitions. Extreme conditions can be defined as something very different from some common environmental conditions. It can be subjective as compared to human predilections, which most people define it as. Or an objective definition can be as compared to the environment where life first developed. That will probably make us extremophiles, because life developed probably under very extremophilic conditions. They can also be defined as extreme values far from the median of any particular environmental property. So it's something between the subjective and the last definition, what we really use today. But the first time the term extremophile was used was in 1974 to designate any organism that can grow under environmental conditions that are usually fatal to most eukaryotic cells. So this is not so different from the last definition I found in the last review on extremophiles from 2003. So the current definition is now extremophiles, organisms which permanently experience environmental conditions which may be considered as extreme in comparison to the physical-chemical characteristics of the normal environment of human cells. Okay, I will first look a little bit at different extreme environments. Physical extremes are, of course, temperature, pressure, radiation. We can talk about biochemical extreme conditions, pH, salinity, desiccation, and some people also include extreme oxygen tension as a factor, redox potential, or even presence of toxic compounds. Biological parameters, we can also define nutrition, extreme nutrition, as an extremophilic property. For instance, organisms that feed on substrates that are very inert and very difficult to attack, like methane oxidizers or hydrocarbon oxidizers, or organisms that have very little access to nutrition. Organisms that get a slice of bread only once a year would be quite extreme. Okay, we'll see a little bit about the different, look a little bit at the different categories of the extremophiles. Temperature as a factor. The heat-loving organisms are called thermophiles, so the most extreme of them are called hyperthermophiles. They grow optimally at temperatures above 80 degrees. And the record today is really 113 degrees for cell growth. Not optimal temperature. Psychophilic organisms grow optimally below 15 degrees, and the lowest temperature for which life has been, the growth has been recorded is about -2 degrees Celsius. The high salt environments are found in salt lakes, solar saltons, and in brine. Organisms growing there are called halophiles, salt-loving. Barophilic organisms have been isolated from the Mariana Trench. They are also called piezophilic. They love high pressure. The Japanese, I think, are the only one that are really isolating true barophiles by now. So they have isolates that start growing only at 500 atmospheres. They don't grow at lower pressure. So the reason for that is a mystery.
Does high pressure mean high temperature or high pressure and room temperature? Or?
Well, in Mariana Trench it's cold, so they are cold at it.
Okay.
Yeah.
How deep?
Oh, it's almost 11,000 meters.
Yes.
Mariana Trench. Acidophiles grow at extremely low pH, almost down to pH 0. Alkaliphiles at high pH. I think it's up to around 12. Oxygen can be considered as an extreme factor. Most microorganisms really on Earth, they cannot tolerate oxygen. Oxygen is a quite toxic substance, so not the oxygen molecule itself, but the derivatives of it. And in some places there might be a very high oxygen tension, like in the subglacial lakes, at least in Antarctica. I've heard that the water there is super saturated with oxygen, so that they are probably adapted, those organisms that have adapted to high oxygen tension. Radiation is a factor. There are highly radio-resistant bacteria living in soil, almost everywhere. I was in Chernobyl last year and visited the reactor that exploded there in 1986. The microbiologists in Kiev, they have isolated very radio-resistant fungi from that, inside the reactor, inside that block. And they have been exposed there for more than 20 years, almost 30 years. And not only are they resistant, but they said also that the fungi they had isolated loved that radiation. They actually looked like they grew to the radioactive source and migrated to the radioactive source. But this has not been published yet. I'm a bit skeptical about it. Yeah. Toxins and heavy metals. You find microorganisms, extremophiles, everywhere. Okay. Now, how do they cope with extreme conditions? Hyperthermophiles have been studied for quite a while now, and a picture is emerging. The proteins in hyperthermophiles usually have very high intrinsic stability, so they are stable by themselves. By increased and optimized intermolecular interactions and packing. I can't go into detail of that. And they are less flexible than proteins from mesophiles. And typically, they have a lot of ionic interactions in the proteins. Ion bonds, just like you find in crystals. Membranes also need to be stabilized. Hyperthermophiles quite often contain in their membranes tetraether lipids, which form a lipid moon layer as compared to a lipid bilayer in other organisms. So this lipid moon layer membrane is more tolerant to high temperature. It doesn't disintegrate that easy at high temperature. So that is probably also a quite important factor. salinity. Halophiles grow in environments with 5 mole of sodium chloride. The problem they have is to keep the water inside, because water will tend to leave the cells. So halophilic archaea have solved this problem by accumulating potassium chloride. So they accumulate up to 3 mole of potassium chloride, and thereby they have a isotonic cytoplasm. But they spend a lot of energy on that, taking up so much.
Cytoplasm means what exactly?
Cytoplasm is what's inside the cell.
Okay.
So it's energetic, costly to live
Yes.
in a cold environment?
Yes, it is. It costs energy to be growing in the extreme environments. Halophilic bacteria have another solution. They don't take up salt. They synthesize what we call the compatible solutes or osmolytes, like certain amino acids, or it can be even carbohydrates, disaccharides. So they accumulate this in the cytoplasm, making them isotonic. Alkaliphiles, I think I will skip that slide. It's a too bit detailed for this audience maybe. So I will say a little bit what we are doing. We don't have any hot vents or any hot springs in Norway, but we get a lot of samples from the North Sea oil wells, which we have a lot of, and down there it is quite hot. The temperature ranges from 70 to above 100 degrees in the oil wells. So we have been working with samples from these environments quite long. I haven't participated in all this, but this is some of the organisms that have been isolated in our department. And it is now accepted as a fact that organisms grow down in the wells. They belong to indigenous microflora. 10 years ago, people were very skeptical. 15 years ago, nobody believed that there could be live organisms down there really. But now it is more or less accepted as a fact.
Is this in the oil or in the water?
Yeah, we recover the bacteria from the water, the produced water. So it's a mixture of water and oil coming up. Yeah, so we have isolated organisms with different nutritional properties, sulfate reducers, the thermogens and fermentative bacteria. So these are all quite thermophilic. Sulfate reducers, they feed mostly on organic acids. The methanogens use hydrogen and CO2, they are autotrophic. The fermentative bacteria feed on things like carbohydrate and proteins. There cannot be much of these compounds down there really, but anyway, they like it.
What does new genus mean? That before they were all male and now we found female? Or the other
New
way around?
genus, now it means a new genre, or a new, it doesn't have to do with sex.
Okay,
It's a new group,
okay.
it's a taxonomic
But
unit.
it's not a species, which is a different kind of group or one.
It's higher taxa
Okay.
than a species, almost like a family. Okay, this shows just the depth of the oil bed. So they range from 1,500 meters down to 4,500 meters in the crust. So we have, and this shows basically the tree of life. And the extremophiles, most of the extremophiles are within this red line. So we have isolated organisms from most of these groups, all these groups actually, except for the halophiles, and also from the gram-positive bacteria and protobacteria. So the diversity seems to be very high. We are covering a lot of the tree of life. This shows the results of molecular analysis of the diversity. We have also extracted DNA directly from the produced water, and using certain gene technology method, we can find out what organism this DNA come from. And we can, using that by searches, find what are they most similar to of cultivated organisms. So the organisms we find using molecular techniques are different from one we get when we cultivate. So there's a lot more to get, a lot more organisms that we can cultivate. So we will try to get as many as possible of these groups. Yeah, what are they feeding on? We have never succeeded to get any organisms growing on petroleum or hydrocarbon. So they cannot use the oil. That is impossible. I don't think so. So they feed on hydrogen, they feed on organic acids, proteins, on carbohydrates. So this model has been proposed by Carsten Pedersen and was shown in the previous talk. What I also believe is that hydrogen and CO2 coming from deep down in the mantle drives this ecosystem. So we have organisms using hydrogen and CO2, building up biomass. And then we have fermentative bacteria that probably degrade these polymers back to hydrogen and CO2. So it's probably a quite complete ecosystem. Yeah, this is what we are doing and what we plan to do. We want to isolate more organisms and to analyze more than adaptation mechanisms to the extreme temperatures at molecular level. Many of these organisms can also have can be utilized for technological purposes. And finally, we would like to find out how the complete ecological system down there works. Thank you.
Thank you very much. You're trying to talk about about these things. You find something more extraordinary, like the 500 bar thing. Actually, you don't look very far for streamophiles. I think depending on how much acid ingestion you have, but there's some bacteria in your stomach which is about 2 or 3 pH of 2 or 3, isn't it? So we're running with the streamophiles inside us, I think.
Yes.
Questions, please. Sorry, what were you first, Anya? I didn't see who raised a hand, but Anya, go ahead.
Thermophiles, which are at the upper end, above 100 degrees. So they are associated with the high pressure because you cannot have water at 113. So is there high pressure to keep the water from
Yeah,
boiling,
if you
or-
go above 100 degrees, you have to have pressure, of course,
Yeah.
yeah. But we blow them up to 95.
So how much
without-
higher pressure do you need? Do you need like 2 amperes or a lot more?
Oh, I don't think
Because
so.
I was thinking
We
like both
have never
thermophiles
gone-
and whatever
yeah.
what they
So
call
just an equation.
pixophiles. Yeah.
This is question for the physicists, but we have not grown them above 100.
It's the closest apparent equation. Sorry, next.
Especially in the case of these radiation file things, how do they get there? Do they get there by evolution, in situ, or do they get there from elsewhere, from some other reactor, so to speak?
But these organisms living in soil everywhere, they're probably.
Then it must be some evolution issue here, if they really like radiation.
Yeah, well, the organism from this Chernobyl block, there must have been maybe an evolutionary process going on there.
And if that's the case, then it should be possible to trace it down using DNA analysis, of course.
Yes, it should.
And that has not been done?
No, not yet.
No, that was my question as well. Would it be some heritage from natural reactors, or do you think that some organisms are so extremely radio tolerant?
Yeah, that could be. Nobody knows why this Deinococcus in the soil is very radiation resistant. It could be that it is exposed to radiation sometimes, so it has been exposed a long time ago and still have this property.
Helps for other types of exposures, perhaps.
Yeah.
I just would like to comment on this. Very often these radio tolerance is related, well, they have this radio tolerance because they have very good repair mechanisms of their DNA, which is not necessarily developed to repair radiation damages, but which just help them in case of damages coming from radiation.
Yeah.
This is at least for Deinococcus, which has been also isolated from internal parts of reactors.
Mm.
Originally, they have these extremely good repair mechanisms, and then this selects for these types of organisms to be present in these environments.
Yes, I guess they have all the kind of repair systems that are known.
Well, you have naturally you have parts on Earth where you have a lot of radioactive material, and in these environments could select for organisms which are very good at repairing their own DNA.
Could I use my position as chairman and ask a question? It is a really fundamental question. It's always said that the existence of extremophiles means that it must be much easier to have life in extreme conditions on other planets like Europa or whatever, or the moons, than we previously thought. But I've never understood that argument, and I'd like to comment on it, because we think that things have got into extreme conditions because they've just travelled slowly over and found this niche by evolution, which is a question that was asked before. Can you show that life could have developed? It seems these things actually developed under extreme conditions, and what we need to be able to show, to use the argument extremophiles are to do with astrobiology in that sense. I mean, they obviously are in some other sense, but this is a crucial point. I wonder what your comment would be.
Yeah.
Or a crucial point.
I think, and many people think that life developed under in an anoxic atmosphere and the temperatures around 100 degrees. And then all organisms have adapted to colder temperatures and to oxygen.
But is there any sort of DNA or genetic way of showing that these things really developed there rather than migrated to there because they were pushed out, you know, just by Darwinian evolution, just by natural selection, or found more extreme conditions bit by bit? But rather they actually developed at, say, 500 atmosphere or something exotic.
You can say the hypothermophiles, all the hypothermophiles, they are very deeply branching organisms in the tree of life. So you can, that indicates that the first organisms were hypothermophile.
So there is DNA evidence.
Yes.
Right.
Yes.
Okay.
Yes.
That's a good answer to that question. Sorry.
I have a comment to that. If they're in the root of the tree, I don't think it indicates that they are the first organism. They may be the only organism that survived the last catastrophe. So there may have been something else that developed in nicer conditions. The conditions that thermophiles are in tend to be very difficult for forming proteins or RNA. So it might have been something else that formed first and then it went through this bottleneck.
Yes.
Where only these guys survived.
Yes, and also where to place the root of the tree is also quite controversial.
Yes, sorry.
Just a short comment on this radioactivity. You said that they are growing towards the radioactive.
Yes.
So maybe it is so that the neutrons that are coming from the reactor are producing some chemicals that these organisms are using. That may be the...
Yeah, that could be the explanation, yes. And not the radioactivity in itself, yes. That's a good point.
Well, presumably some radiation damage is going on. Perhaps we ought to pass on. Sorry, I hate chairman to get out of time like I'm doing.